we have seen this is the block diagram of a power supply circuit. So we will be having a transformer, then rectifier, okay, and then after rectifier we need a filter. So once we have applied the filter, after that filter we will place a voltage regulator, and then finally we will be getting the output voltage, that will be a DC power supply voltage, okay. So rectifier output we have seen, either it could be a half wave rectifier or a full wave rectifier. So once we have obtained the rectifier output, we will use some filter circuit to smoothen this half wave or full wave output that we have got from the filter circuit, okay. So we will use some filter circuits. So basic filter circuits, what basic circuits are there used basically for filtering, so we will see that, and then we will see the next what is clipper and clamper circuit. So that is like called wave shaping circuits, that are basically one of the example of diode circuits, okay. So first of all we will see filter circuits, what is the filter circuits are, and then we will go with the clipper and clamper, okay. So the role of filter circuits is like whatever the rectifier output is there, we will pass this rectifier through output by using through a filter circuit, and then whatever output we will be getting, that will be somewhat less, you can say, having less ripple. So basically in rectifier outputs we have seen different outputs. So rectifier outputs are like a half wave rectifier output, that will be this like this, and in case of full wave we will be getting this, okay. So our motive is to have a DC output, okay, but we are getting, so DC output, so DC output is basically this. So DC will be like, this is an example of a DC voltage. So DC voltage means the voltage should be constant with respect to time, okay. So if this is the time and this is the voltage, so output voltage should be varying, having a variation that is 0 with respect to time. So it is almost, or it is constant, that will be a DC. So we require a DC output voltage, okay, but after rectifier we will be getting output that will be having some positive DC. So positive DC means equivalent DC if we calculate, so there will be some positive DC value. So here also some positive DC value. So here in case of here the DC value is Vm by pi, we have seen. In case of full wave rectifier, Vm by pi, this is 2 Vm by pi we get in case of full wave rectifier DC value, okay. So we need to have a constant value here in a half wave rectifier. So we will use some filter circuits. So basically this filter circuits role is to smoothen the rectifier output basically, okay. So here in rectifier whatever output is there, this output is basically, suppose it is in form of current. So this is having the component of DC value, it is having some DC value, along with that it is having some AC value also. If we are dealing with like it is a current, so it could be a current or voltage, okay. So if it is current, it is having a DC component as well as the AC component, even after applying this rectifier circuit, okay. So our motive is finally in filter circuit we need to have only the DC component, okay. So we are going to filter the AC part of the output of rectifier. This is the motive of filter circuits. So these filter circuits are basically implemented by using two different methods. So one will be basically by using the inductor. If we are going to use inductor, then we can implement this filter circuit, or instead of inductor we can even use the capacitor also. So inductor filter, inductor we are using means we will be calling it inductive filter. If we are using capacitor, it will be capacitive filter, okay. So we will start with inductive first. So here, if inductor is there, its resistance offered by this inductor is basically the inductive impedance. We call it by using ZL. Okay, so ZL is the uh, inductive reactance basically. So that is a function of frequency. It is a function of frequency is there. So it is basically given by, okay, omega L, this or WL we can call it. So this omega is basically the 2 pi f into L. Okay, so this is the resistance offered by an inductor. Okay, so from there, so what would be the circuit? We will see from this explanation, like how the reactive inductive reactance basically depends on frequency. Based on that, we will be deciding the circuit. Like the circuit should be in series with the output load resistance or in parallel with the output load resistance. So that will be basically deciding, like for DC, our motive is we need to obtain the DC and we need to filter out the AC component of the rectifier output. So here the DC is basically, for DC, the frequency is, what is the frequency for DC? If it is DC output voltage or current, what would be the frequency for that? क्या होता है? कितना होगा फ्रीक्वेंसी डीसी के केस में? अच्छा, एसी का फ्रीक्वेंसी कितना होता है? अच्छा, एसी सप्लाई जो होती है हमारे हाउस में कितना? 50 हर्ट्ज. ओके, सो डीसी के केस में क्या होता है? 0 हर्ट्ज. ओके, सो 0 हर्ट्ज डीसी मींस, अभी हमने बताया डीसी क्या होता है? कांस्टेंट, वेरी नहीं करेगा. So if there is no variation, that means frequency is 0. If it is having a variation, okay, if it is having a variation, it is having a frequency. Okay, so if it is having a frequency, it will be an AC. So in case of inductive, this is the inductive reactance that is having a function of L and frequency. But for DC, we know like frequency is 0. That means for DC, the resistance offered by inductor will be equals to 0 because the frequency is 0. That means if some component, some current is flowing, this current is having DC value plus AC value. If it is passed through a inductor, so at the output we will get only the DC, because for DC this resistance offered by inductor is 0. So only DC will be passed, and if this resistance offered by this inductor is very high, such that it can you can say stop the flow of AC component, so at the output we will get only the DC component. Okay, so this is the intuitive part that we will be implementing. So in the rectifier we are getting the output. So suppose this is the rectifier rectifier is there. Whatever output of rectifier will be there, if we are going to connect inductor in series with the output, and then we are getting the load resistance and we are getting the output. Okay, so if we connect this way, okay, so then at the output, whatever output we will be getting, that will be having only the DC component. So here it will be IDC plus IAC, but here it will be only IDC. So in case of inductive filter, we will be connecting an inductor basically in series with the load resistance. Okay, so this is the simple filter circuit. Okay, even this is not having much efficiency. Okay, so based on what is the conversion efficiency of the output to the obtained output, so basically here it is having AC and DC. Here we are getting only DC. So what is the rate of conversion, or we can say what is the efficiency of this filter circuit? That will be depending on the different L and RL values, and also we can get better efficiency by considering some more complex circuits. So we will not go through that complex circuit in this discussion. Basically we will just take the overview, like how the filter circuit basically works. Okay, so This is how we will be considering. Okay, so from there we can say like for DC the resistance offered will be 0. Similarly for AC, some frequency value, the frequency will not be equals to 0. So this ZL will be uh, some finite value. So here in case of the ZL value, like for AC it will be having some resistance will be there. So this resistance will be like, if we are able to have the high frequency or the L value is high, L value is high or the frequency is high, if we make this, then ZL will be high. So if ZL is high, that means the AC component will be filtered out. Okay, so we can see here from here like the rectifying efficiency will be depending on what parameters. So like if we can see, so from here ZL is basically directly proportional to frequency. Okay, and it is also directly proportional to L also. Okay, and if this is the case, then ripple factor. So basically the ripple value, like if ZL is high, then ripple will be less. Okay, that means the ripple is inversely proportional to ZL. Okay, or we can call it like R is inversely proportional to frequency in L. That means if we are going to increase the frequency, okay, the ripple factor will be less. Okay, if we are going to increase the L value in the inductor value, then also the ripple factor will be very less. So our motive is to have low ripple factor. So low ripple factor means the output that we are getting from the uh, rectifier or the from the filter circuit, that will be having minimum AC component. Okay, so that is how we can design any filter by using an inductor. So it will be such that the inductance value should be high. Okay, so that we can get the minimum uh, ripple factor. Okay, also if inductor is there, it is associated with uh, resistance. So it is having a time constant that is uh, basically given by L by R. Okay, so this is a time constant. So also here uh, it should be like whatever this ripple factor is there, it is inversely proportional to the time constant. So from this we can just say like it is it will be L by R, or we can call R by L. So R is uh, that ripple factor is directly proportional to resistance also and inversely proportional to inductor. So overall we can conclude like this R is directly proportional to resistance and inversely proportional to frequency and L value. Okay, so this is how we can design an filter circuit based on inductor. Okay, so an inductor is there, so we should be using a resistance that is of low value and inductor of high value in case of inductive type of filter circuit. Okay, capacitive filter or filter by using a capacitance. So in case of capacitance, the ZC value is given by like 1 by omega c. Okay, that means we can see it will be 1 by 2 pi f into c. So from there for DC we know like f is 0. So f is 0 in case of DC. Okay, so if we put this value, it is implies like the ZC will be infinite for DC. It is implies like if it is infinite means it will be if the resistance offered is infinite, that means it will be like an open circuit. So if a capacitor is there, if we are passing DC value, it will be open circuit. Okay, so it is infinite means we can call it like uh, capacitor will be an open circuit. So capacitance will be open circuited. So if capacitance is open circuited means if this is the configuration, if we are passing this DC plus AC, for DC it will be open circuit, means there is nothing passing through the RL. So if open circuit means the output that we will be getting through this resistance or the load resistance will be 0. Okay, in case of means 0 DC value we will be getting. So DC value output will be a 0 value because no DC is passing. So we need not to connect this capacitor in series with this resistor. So we will not be using this configuration. So the configuration that we will be using is a rectifier is there. Okay. So instead of using in series, we will use it in parallel. Okay. So this will be your capacitor and this will be your load resistance, and here output we will be taking. In this configuration, so whatever current is being flowed, like it is IDC plus IAC. So as we already know, DC cannot flow through this. That means for DC it will be open circuit. So that means the DC will only be flowing through this. DC cannot flow through this, and this C value will be allowing only to AC component. So AC component will be passing through the capacitor, and the remaining DC component will be passing through the resistance. Okay, so this is the motive. Basically we are filtering out the DC and considering the AC component out of the output voltage that we are requiring. Okay, so from there also we can just see in case of like other circuits. So if ZC is there, that is having the proportionality like it is proportional, inversely proportional to frequency. That means if frequency is suppose high, frequency is high. Okay, so in that case we will be having like the ZC value will be low. So if frequency is high, ZC value will be low. So for AC components, so frequency will be high. So for AC component, frequency will be high. That means the resistance offered by capacitor is low. That means the basic principle of flowing a current is like whenever a current is flowing, whatever the minimum resistance it will be getting through that circuit only it will be flowing. Okay, so if we are having a AC component as well as the DC component, so AC component is obtaining a very low you can say resistance path through the capacitor circuit. So whatever the low resistance path will be there, that will only be followed for the current flow. Okay, so for AC component, capacitor is basically providing a very low resistance path than even the resistance. Okay, so the AC component will be passing through the capacitor, and the DC component will be passing through the, this is the capacitor that is having its impedance. So this its impedance is basically having inversely proportionality with frequency as well as the capacitance. If capacitance is high or the frequency is high, then the resistance offered by this will be minimum. So then the AC component will be passing through it. Okay, and in case of DC component, the resistance offered by capacitor is infinite. That means it will be behaving like an open circuit. So it will not be having any effect on the DC, like it will not be passing any DC. So all the DC will be passing through this circuit only. Okay, so this is the basic filter circuits. So as the name suggests, it is a clipper circuit. So it is clipping whatever input we are going to provide to a circuit. So clipper its role, these circuits are basically called wave shaping circuits. Wave shaping circuit means whatever waveform we are giving as the input, it will do some type of modification to the circuit, to the input, and it will provide the output that will be having some different uh, orientation. The waveform is having some uh, distortion or some loss will be there, and that will be based on our desired requirement. So whatever our requirement is there, we are going to have the, we need to modify whatever waveform is given. So if we are going to modify given waveform based on our desired requirement, we will be using the clipper and clamper circuits basically. So these are called wave shaping circuits. So whatever waveform is there, we will be going to shape, or we are going to give another form of that waveform. Okay, we will see that like how it is basically obtaining. So clipper circuit is one of the wave shaping circuits. It is used to clip, it is used to clip or cut, or we can say a shape. It is going to clip some portion of an input waveform. Okay, so it is going to clip some portion of an input waveform. So it is going to clip some portion of the input waveform uh, based on based on the diode on and off characteristics. Okay, so we are going to use a diode circuit to remove, or you can say to remove some part of the waveform that is given as an input. So the basic circuits, basically this clipper circuit is also uh, divided into two different types. So basically the types of clipper circuit. So the one is called series clipper circuit, and the another one is parallel clipper circuit. So the series means we are having the load resistance in series with the diode. So we are going to have uh, a diode, and there will be an output load resistance. So in series means we are going to have a diode in series with load resistance. Okay, so here parallel means diode parallel with the load resistance. Okay, so the first one is series clipper circuit. So this is the example of a series clipper circuit. We are having a diode, okay, connected with a load resistance R, and we are getting the output from the load resistance. Okay, so whatever the voltage across the load resistance is there, that we will be getting. So this input is the input waveform, that is an AC component, or whatever voltage we are giving. So it could be AC or DC also. So sometimes like we have just we are going to analyze the AC components only, but in some cases like it will be giving you out some DC component, then how it will be behaving. So in DC component, in the previous classes we have already seen like that how the diodes will be working, behaving like once we have applied the DC component. So here we are applying the AC component and how it is going to vary. Okay, so if it is an ideal diode, if diode is ideal, if this is the waveform we are providing, so this is a, okay, what is it, rectangular or square wave we can call it. Okay, so this is an square wave we are providing as the input, and we need to analyze what could be the output. So here, so we have already seen like it is an ideal diode, so it will be on. So ideal diode will be on when input voltage is greater than 0. So if input voltage is greater than 0, the diode will be on. If input voltage is less than 0, it will be off. Okay. So this is the input. With respect to that, the output is given. So here how the output is basically defined. So here with respect to time, it is like it is initially it is having a value of v, okay, for some time. Okay, so this is suppose t by 2 and this is t. So for t by 2 time, it is having a value of v that is greater than 0. So this v is greater than 0, so this condition satisfies, so this diode will be on. If it is on, it will be like a short circuit. Okay, so if diode is on, it will be a short circuit. So whatever input we have applied, the same input will be appearing at the output across the resistor. Okay, so whatever in the positive half cycle or from 0 to 2 t by 2 time period, the input waveform is positive, so this positive voltage, the same voltage will be appearing at the output. Okay, is it clear? Similarly in the negative half, so as we are going to apply this input voltage that is less than 0, so this is the 0. Okay, so here we are going to apply a less than 0 value of the input voltage. So if it is less than 0, that means the diode will be off. So if it is off, so in off case, the diode will be behaving like an open circuit. So if it is off, it will be open circuit. So whatever voltage drop will be there here is basically it will be a 0 because there is no current flowing. If no current is flowing, the voltage drop across the resistance will be 0. So the output that we will be getting is a 0. Okay, so in on case, we will be getting whatever the input we have applied, the same input we will be getting at the output. In the off case, the output we will be getting is 0. Okay, so this is how we will be shaping the circuits. So this is the second example. Okay, so triangular waveform is given. So we have given this is the waveform. So whenever the input voltage is greater than 0, that same will be appearing at the output. If it is less than 0, that will be clipped off. So that is below the 0 level, that is being clipped off basically. Okay, so here the clipping is being performed. Okay, so this is the simple example. So another example we will see. So if this was the case of simple diode, a single diode is there. Here we are using a diode with a supply voltage. So another a supply voltage is being used here basically. So a supply voltage is used means we are providing an extra voltage across this diode. So this is the input and this is extra voltage, and you can just note it down the sign. So the sign of the voltage that we are applying is important. So this is positive and this is negative. That is the case of input voltage that we are applying. But in case of the DC supply voltage that we have applied, that is in opposite direction to whatever we are applying. So if we consider the KVL, it will be like whatever the voltage is there, that is in opposite direction. So if it is in opposite direction means, if suppose this is the waveform, input waveform. So in this case, our main motive is basically to find out whether the diode is forward bias or not. Okay, so if it is forward bias, it will be behaving like a short circuit, and then with respect to that we will be getting the output. If it is open circuit, the current flowing will be 0, and then with respect to that we will be getting the output that will be 0. Okay, so we need to first decide what is the current flowing through this circuit. So for that we need to see in what region this diode is working. So this is the input voltage we are giving. So here suppose input voltage in the previous case, as the input voltage was greater than 0, it was on, but in case of here it will not be so. Okay, so here suppose we have started with 0 voltage. So once we are giving with 0 voltage, or suppose some 1 voltage is there, suppose this is 1 voltage and this one V is some voltage that is 2. So even if we are applying some positive voltage but that is less than 2, then this diode will not be turning on. Okay, so diode will only be turning on when we are able to apply a V voltage greater than the V voltage. So V input will be greater than the V voltage, then only the effective voltage across this diode will be positive or negative. Okay, so if we consider from here, so suppose we need to find out the VD value, or we can call it like the VD value. So if suppose this diode is on and across this there is a VD voltage drop is there. So by using this we can just see like what is the KVL. Okay, so in that case we can see like the VD is basically proportional to or having some relation with V input minus V. Okay, so if V input minus V is greater than whatever the voltage is requiring, basically in case of the ideal, so the VD value is 0. So in that case, if in ideal case it will be 0, so if V input minus V value is greater than 0, then only the diode will be on. Okay, so it is like we need to move in the positive direction from 0 to some positive value, such that if V value, suppose this is the level of V value, so this that whatever voltage we have applied, so this is the V. So as we are moving beyond this V, then only the diode will be on. So for this time duration only the diode is on. Okay, so on condition of diode you are getting that. Okay, everyone, are you getting like when the diode will be on? So our main motive is to find out like when the diode will be on. Okay, so to turn on this diode we need to apply a Vi input that is greater than V voltage. Okay, so suppose this is the region, then only this, for this region only the diode is on. So if for this region only the diode is on, the output will be, so output will be whatever voltage is there. So suppose this is the plus and minus, this is V output. So if this is on, it will be short circuit. So the output circuit that we can get from here is like, and this is uh, the voltage. Okay, so if it is on, some current will be flowing. With respect to that we are going to apply the KVL. Okay, so KVL is basically how we are going to apply, like whatever the existing, suppose this is the voltage, whatever existing voltage is there plus V, so plus V input we will be writing. The exiting voltage is, the sign basically is negative, so negative V voltage will be there. So exiting voltage in the direction of current is like exiting sign is negative, so negative V output will be there, that will be equal to 0. So this will be the case. So output voltage that we will be getting is from transferring, we can get like it is V input minus V. So if the diode is on, the output that we will be getting is V input minus V. So in case of like if it is positive, like it is turning on, so if it is on, we will be getting the output that will be such that we are having output voltage that is V input minus V. Okay, so to decide what will be the switching point at which the diode will be on, we will be making like the current is flowing is 0, and at that time the voltage across the diode is 0 because it is on. If it is on, the voltage across the diode will be 0, but it is the condition of even the same current that is flowing. So initially if it is off, the current will be flowing is 0, but there is some point. So if it is like we are applying, so here the current is flowing 0, here the current is flowing 0, but there will be a point at which the current flowing will be some positive value. So to identify that level or that triggering point, that is there, such that the current flowing will be a positive value, for that condition we will be putting the ID. Suppose the ID is flowing through 0, this circuit is 0, and at that time the diode is on, then the KVL if we are going to apply, then that case that voltage will be basically given by the V voltage. So from there we can get like the Vi will be equals to V. That means for Vi input voltage equals to V, the diode will be on. Okay, so this is how we will be deciding the transition voltage or the voltage at which the diode will be turning on. Okay, so once we have obtained, like once we are applying the voltage, input voltage greater than Vi, the diode will be on. So with respect to that, the output we will be getting is V input minus V. Okay, so this is the region. This is how it is given, like this is the maximum voltage and this is the V level, and before this below this V level the diode will be off, and above this V level the diode will be on. Okay, so for what time it is on, that will only be appearing at the output. So the output waveform, if it is on, so this is the case of on state of diode. If it is on, the output that we will be getting is, initially for the time the diode is off, we will be getting a zero output, and when it is on, the only the that portion we will be getting at the output. So only this portion is appearing at the output basically. Okay, so for which time the diode is on, so this is only appearing, but its DC value has reduced, it is shifted to downward. So this is the waveform that we will be obtaining. Okay, and in the negative half itself, it will always be in reverse bias, so it will be having a zero output. So the maximum output voltage that we will be getting is whatever the maximum voltage was there minus the DC supply voltage we have applied. Okay, so this is how the clipper circuit will be having. So this is a series clipper with a supply voltage. So even if suppose is the case is like, another case is, suppose this is the input. Okay, and suppose this is 5 volt and this is the V input that we are applying, and it is 15 volt, this is 0 and this is minus 15 volt. Okay, and this is 5 volt. Okay, so in this case what will be the output, anyone? When it will be on and when it will be off? Yes. So to draw that, we will basically do, like whenever the input is there, whatever input voltage is there, with respect to that only we will be drawing. So suppose this is the input voltage and this is the 10 volt, oh sorry, 15 volt, and this is minus 15 volt. With respect to that, we consider the output. So if it is 0, if we are applying the 0 voltage across here, then also it is positive. That means this diode is on because it is already having a 5 volt supply. So even if the input is 0, then also this diode is on. Okay, so it will be on. So whatever input voltage is there, okay, so whatever this voltage is there, the same we will be saying like it is on. So suppose it is on, in that case this is the output. So the output will be basically the Vi plus 5 volt. Okay, so if we apply it is, if it is on, it will be short circuit, then we will, some current will be flowing and we will be applying the KVL. So if we apply the KVL, we can get that output voltage will be given like V input plus 5 volt. So from there we can see, if it is 0, but we will not be getting the output from 0, we will be getting the output from the plus 5 volt. Okay, so this is the plus 5 volt. Suppose this is the plus 5 volt, so we will be getting the output not only from 0, it will be getting from the plus 5 volt, and we will be reaching to the maximum plus 5 plus 15, that is, that maximum value will be going up to 20 volt. Okay, so now in this case also it is whatever output we are getting, but suppose we are going to downward. So if for this, what will be the output below this? The output we will be getting is, suppose we are applying minus 4 volt. If minus 4 volt we are applying, then we will be getting the output is 1 volt. That means we will be getting output till the minus 5 volt. So till we have applied minus 5 volt, we will be getting some output, and that output will be like at minus 5 volt it will be 0, and below this minus 5 we will be getting like the diode is reverse bias. The diode will be reverse bias only when we are applying the below minus 5 volt. Okay, so till minus 5 volt the diode will be forward bias, because this 5 volt will be cancelled out and 0 will be applied. Okay, so up to here, so from here up to here we will be getting the 0, but after that again we will be having this. So if we extend this, it will be like having some positive value. Okay, if we extend this waveform below here, so this is how the waveform will be appearing. So based on the direction of, so in even the gate also, this clipper and clamper circuits can be asked, and in that they will be playing with whatever the supply voltage it is providing. So if it is providing a positive or negative in respect to the input or with respect to diode, that will be deciding the output voltage level. Okay, so that is basically uh, the series clipper. The next one is parallel. So basically parallel clipper circuit means we are getting the output in parallel with the load. So whatever load resistance is there, there is some load resistance also. So if this is the load resistance, so whatever voltage across the load resistance will be there, the same voltage will be across the diode. So if it is either the diode voltage, the voltage across the diode, or the voltage across the load resistance. So here load resistance is in parallel with the diode. Okay, so basically here it is not written like whatever voltage is there, if because this diode will be basically replaced by the either short circuit or open circuit. Okay, so if it is open circuit, whatever voltage will be there at this, if it is open circuit, no current will be flowing, so whatever voltage across this input will be that will be the output. So this is the case basically. So we can just redraw. So here this is the diode, and here a load resistance is there. So load resistance is parallel with the diode. So whatever the load resistance voltage is there, the same voltage will be across the diode. Okay, so that's why it is not written here. These are like equivalent circuits. Okay, so from there we can just provide like this is the input, and with respect to that we can get the output. Like, so if we are providing the input, so for positive voltage the diode will be on. So if it is on, it is short circuit. So if it is short circuit, then the output will be 0. Okay, so if in the negative side it will be reverse bias. So if it is reverse bias, it will be open circuit. So if it is open circuit, so whatever voltage we are applying, the same voltage will be appearing. Okay, so in the previous case it was negative clipping, in this case it is positive clipping. Okay, so the previous was the example of negative clipping. So negative portion was clipped off, here the positive portion is being clipped off. Okay, so this is parallel clipper example.